Okay, hello class. So I'll be taking you on a lecture. So the course title is General Chemistry and the course code is CHM 111. So I'll be starting with Module 1, which is chemical bonding and intermolecular forces. So here are the core concepts, and you're expected to know the type of chemical bonds, that's ionic, covalent, and metallic. Okay, then molecular shape as determined by VSEPR. Then you're also supposed to know the intermolecular forces, IMFs, and the strength of the IMFs, okay, as dictated by key, so which dictates key physical properties like boiling point, melting point, and viscosity. So these are the core concepts. Take note of the learning objectives. Now to the real world relevance. So at the end of this module, you are expected to know why table salt is a brittle, high melting point solid that dissolves in water, while sugar is a solid but it can be melted and burns easily. Another real-world relevance is why is oxygen a gas at room temperature but water is a liquid. The answers lie in understanding the forces that hold atoms together within a molecule. Within a molecule, that's chemical bonds. And the forces that exist between molecules, these are intermolecular forces. So, and this determines the properties of observed in different materials. For example, the strength of a diamond, okay, or the flexibility of a plastic bag, and even the surface tension of water. Now, to the theoretical foundations. Okay, so we are going to start with ionic bond. An ionic bond is the electrostatic attraction between oppositely charged ions. Oppositely, okay? Cations to represent the positive, while anions to represent the negative ions. So ionic bond is the electrostatic attraction between oppositely charged ions formed by the complete transfer of one or more electrons from a metal to a non-metal. Okay, from a metal to a non-metal. So where do you find the metals? Group 1, group 2, and also partly group 3. Okay, so you can find metals there, residing there. Okay, then so for example, you look at the sodium chloride crystal. So the sodium chloride crystal, you have sodium as the metal and chlorine as the non-metal. So transfer of electrons is from the metal. So the metal loses an electron, and because it loses one electron, becomes Na plus. So that's sodium ion, and the chlorine becomes a chloride. Okay, so that becomes Cl minus, and that's why you have sodium chloride. Now, what are the properties of sodium chloride, of ionic compounds? So one, they have high melting and boiling point. This is because of the strong lattice forces, okay, between the ions. Then also they are hard but brittle. Hard but brittle. Okay, so that means they are brittle. They can be broken. Then they are often soluble in polar solvents. I think I talked about polar solvents. So they are in class. So they are often soluble in polar solvents like water. Also, they conduct electricity when molten or dissolved. So these are the properties of ionic compounds. Now to covalent bonds. The covalent bond is a chemical bond formed by the sharing of electron pairs between two non-metal atoms. So that both atoms must be two non-metal atoms. Okay, and this brings us to Lewis structures. So Lewis structures, I will be considering this in class where I'll be having a general class. Okay, so there we're going to talk about Lewis structure. Okay, now let me move on. So equivalent bond can be polar and non-polar. So remember that equivalent bond has to do with sharing of electron pairs, right, between two non-metal atoms. So equivalent bond can be non-polar or polar. Okay, so take note. Okay, for non-polar you have equal sharing. You can see it there. So you can see there equal sharing. That's for non-polar covalent bond. There must be equal sharing. Okay, and the change in electronegativity is between 0 to 0.4. Okay, the change in electronegativity is between 0 to 0.4. Example, you have hydrogen gas H and H, chlorine gas Cl and Cl. That's chlorine. So that's it with non-polar. Okay, so wherever I see two elements combining like H and H, Cl and C, then that there you have a non-polar covalent bond. You have equal sharing. Okay, now to polar covalent bonds. So for polar covalent bond, you have unequal sharing. Okay, unequal sharing meaning that the change in electronegativity is between 0.4 and 1.7. So take note of it. Unequal sharing because the change in electronegativity is between 0.4 and 1.7. Okay, so example is HCl. Okay, now on to VSEPR theory. VSEPR theory states that electron groups as bonding and non-bonding around a central metal atom will arrange themselves to be as far apart as possible to minimize repulsion. Take note of that. VSEPR theory, that's the valence shell electron pair repulsion theory, states that electron groups bonding and non-bonding around a central metal atom will arrange themselves to be as far apart as possible to minimize repulsion. Okay, so in class, that's I'll be doing a general class. I'm talking about Lewis theory and VSEPR theory. Now let's look at this table. So please kindly get acquainted with this table. So there you have the electron groups, 2, 3, 3, 4, 4, and the likes. But where I want to come in is where you have example there. An example is CO2. Okay, CO2 is linear. BF3 is trigonal planar, that's in shape. You can see SO2 is bent. CH4 is tetrahedral in shape. NH3 is trigonal pyramidal in shape. H2O is what is bent. Okay, so kindly get acquainted with that, and you should also know their polarity. CO2 is non-polar, BF3 is non-polar, SO2 is polar, CH4 is non-polar, NH3 is polar, H2O is polar. So that's water. So you should take note of that. Now to molecular polarity. So a molecule is polar if it has polar bonds and an asymmetric shape. Take note of the two conditions. You must have two conditions. A molecule is polar if it has polar bonds and an asymmetric shape and an asymmetric shape. Okay, now on to intermolecular forces. So intermolecular forces are attractive forces between molecules. So they are much weaker than chemical bonds. Remember, I just talked about chemical bonds. So intermolecular forces are attractive forces between molecules, but they are much weaker than intramolecular chemical bonds. Okay, so example, you can see London dispersion forces. So what are London dispersion forces? They are temporary instantaneous dipoles created by uneven electron distribution in all molecules, whether polar or non-polar. Whether polar or non-polar. So this temporary dipole can induce a dipole in a neighboring molecule, causing a weak momentary attraction. So that's it with the London dispersion forces. Okay. Now next with the IMFs, look at the dipole forces. So these are attractive forces between permanent dipoles. To take note of that, permanent dipoles of polar molecules. Permanent. Okay. The positive end of one molecule is attracted to the negative end of another. Okay. So take note of the examples there. So I could ask you, so you can have an example, SO2 HCl. Okay. But in for London dispersion forces, this is present in all molecules and atoms, while for dipole forces, this is present only in polar molecules. Only in polar molecules. So take advantage. So take note of the differences. Now to hydrogen bonding. Now to hydrogen bonding. So hydrogen bonding, here we have a special type of dipole force that occurs when hydrogen is covalently bonded to a highly electronegative atom, and these are nitrogen, oxygen or fluorine. Nitrogen, oxygen or fluorine. So for hydrogen bonding to exist, you must have fluorine, oxygen or nitrogen there. Okay, and these are highly electronegative elements. Okay, so example, you have water, ammonia, hydrogen fluoride and DNA based pairing. So these are where situations of molecules where you can find hydrogen bonding. Now let's link the concept. Okay, let us look at the concept that we've just considered. So the basic concept of why we are even considering bonding is we want to look at how the bond type affects the physical property of a material. If a material is strong, why is it strong? If a material has a high boiling point, why does it have a high boiling point? If a material is brittle, why is it brittle? Okay, so you can trace it to the type of bonding that exists. Okay, that's intramolecular or intermolecular forces. Okay, now let's look at CO2. CO2 has covalent bonds. The shape is linear geometry. It is a non-polar molecule. For CO2, only London dispersion forces are present, and thus it has low boiling point. It is a gas at room temperature. But for H2O, also covalent bonds, bent geometry, but the molecule is polar. The molecule is polar, okay, and hydrogen bonding exists, okay. It has very strong intermolecular forces. So these intermolecular forces are directly responsible for the high boiling point, okay, observed for water. Now let's look at common misconceptions. So molecules that have hydrogen bonding are any molecules with hydrogen. That is false, okay? That's not true. So hydrogen bonding only occurs when hydrogen is bonded directly to fluorine, oxygen, or nitrogen, okay? Now another misconception is the bond in hydrogen chloride is an ionic bond because it has H plus and Cl minus. That is false. That is false, okay? So HCl is a polar covalent bond. It is a polar covalent bond. So now number 3, IMFs are just weak chemical bonds. No, IMFs are completely different from the chemical bonds. That's intramolecular chemical bonds. Okay. Now to the fourth misconception. CO2 is polar because CO is polar. No. Remember we said for something to be polar, okay, there are two conditions that must be met. Okay. So one, it must have polar bonds and an asymmetric shape. Okay, asymmetric shape. So that is not what you have for CO2. Okay, so that is why CO2 is non-polar. Now we move to the second module. We will look at kinetic theory of matter. Kinetic theory of matter. So here we'll be looking at some core concepts. So there are some core concepts that we'll be considering. Okay, so 1, all matter is composed of particles in constant random motion. 2, the energy of this motion is kinetic energy, and the average kinetic energy is directly proportional to temperature. So 3, the state of matter, that is solid, liquid, or gas, is determined by the balance between the kinetic energy of the particles and the strength of the intermolecular forces between them. Then also we'll be looking at the Maxwell-Boltzmann distribution curve. Okay. Now, why are we even looking at this?